Hello everyone and welcome to the second lecture on nonlinear optics. In the first lecture, I have introduced to you some of the basics of nonlinear optics. We have understood what nonlinear means in the context of optics. We have tried to understand in what ways nonlinear optics is different from linear optics. Linear optics is something that we are very familiar with. We have observed a lot of linear optical phenomena such as refraction, reflection, and we all know what absorption and scattering is. And in the current class, we'll try to build on top of that, and we'll try to build the physical understanding of it. We'll do some mathematics, and by the end of the class we'll be equipped with all the mathematical tool to understand nonlinear optics. And let's dive right into it. And some recap from the last class. In the polarization in the context of nonlinear optics is slightly different. There are some nonlinear terms. So what I mean by that is, in linear optics, polarization is let's assume scalar for now. Polarization is directly proportional to electric field. Here chi1 is electric susceptibility. But in nonlinear optics, we have some additional terms, such as we can have terms like E square and so on. Here, polarization is proportional to electric field. Of course, that's the linear domain. But when we have strong enough electric field, we also get all of these nonlinear terms. And in the last class, I have introduced to you some of the nonlinear effects. One of the effects I have introduced is SHG, that is second harmonic generation. That's a Kaito process. And also we have talked about SRS, stimulated Raman scattering. It's a Kaito process. But there are multiple other effects as well that we'll be discussing throughout the course. Like in the Kaito, we have SFG, that is some frequency generation, and then here we have things like third harmonic generation, four-wave mixing in general, or Brillouin scattering, and etc. etc. We'll talk about all those effects one by one. But before we go any further, let's recap some basics of linear optics. In that way, we'll be able to build a mathematical basis of the wave equations and everything, such that we'll be able to go to nonlinear optics and build the mathematical basics of it. Then we will be able to do some calculations, and we'll solve some numericals, and also we'll do some simulations as well. And to do all of that, in order to understand the applications of nonlinear optics, like we had discussed some second harmonic generation in the previous class, but how to optimize such processes, what crystal to use, how to focus, what are the laser properties, like what are the spectral width of the laser we should use, and things like that. uh, and how to optimize all those processes. In order to understand that, in order to understand the engineering aspect of it, we will need to understand the mathematics, and we'll start from Maxwell's equations, because that describes everything related to electromagnetic wave. And let's start with that. I'm sure you have already come across Maxwell's equations, and let me just recap. And for electromagnetic wave, what is very important is, um, of course, the electric flux density. Here we have D, which is electric flux density. Let me write it here. You might already know that Maxwell's equations are written in terms of electric flux density, and of course you might have already seen the Maxwell's equations in terms of electric field only, but then these polarization effects are very important here. And if we, in those cases, if you had already seen Maxwell equations in terms of E only, in those text, they might have skip polarization, and that's very important because that will give you the response of the medium, and that's where we get the nonlinear effects, right? So here, electric flux density consists of two terms, first and second. Second is the polarization. And why do we get two terms? So what's the physics of it? So first term is coming from free charges. So what I mean by free charge is literally they're not bound to any atoms or any metals or so. So they're free, like in metal, like electrons can flow freely, right? So those are free charges. And here we have polarization effects, which are due to bound charges. Okay, and that's where we get the response of it. So bound charge could be like electrons in a atom or molecules. If there is a electric field, it tends to polarize those inherent charges. So in a way, polarization gives you how the material or the medium will react if there is an incident electric field. So that's very important. And in linear optics, as I already told you, polarization is nothing but chi1 times electric field. And linear optics, like interference, it's in let's not talk about interference first, like uh, effects like refraction, reflection. So suppose one beam is refracting in going from one surface to another, it won't get affected if there is one more beam, right? The same goes with reflection. But in interference, it looks like that it's being affected by other beam, but it's just superposition. It's just two beams are adding up. They are not inherently affecting one another, right? So in simple terms, you can say in linear optics, light don't talk with one another. Talk is a very loose term, it's not scientific. Yes. But you get the point, right? But in nonlinear optics there can be, I mean, some energy exchange. So linear optics, so these are linear optics. Then here lights don't talk with one another. And nonlinear optics, there is a some energy exchange, and that is through polarization. And how so we will understand? So we just deviated a little bit from Maxwell equation, so let's get back to Maxwell's equations one by one. And the first one, that Gauss's law. Just a recap, I know you might have already studied all those things, and here we are writing in terms of flux, electric flux density. And here it's charge density. You all already know this is charge density, but what is important is that it's free charge density. And second one, very important, we have Maxwell's Faraday equations, very famous. You might have come across these equations in your like class 2 schooling and all. I mean, it's very basic. Let's try to understand what it means, because this Maxwell Faraday equation, that was something observed by Faraday first, so it gives you electromotive force if there is some maybe changing magnetic flux. So that's very exciting, right? It's due to change of magnetic flux. You can get some electromotive force. So just let's deviate from our EM theory basics to this Maxwell's Faraday equation. So we have this, right? Then I'm just taking a area integral. Here we have sorry, let me try. That's area integral. Then we can use something called Kelvin-Stokes theorem, which can be used to convert area integration to line integration. So what we get from here is the L. So I'll just write the theorem here for reference. And here let's take out the time derivative and integrate the magnetic field over an area. Here we have dl, and this part is nothing but magnetic flux, right? Magnetic field over a area integration, that's flux. Then we can just write it as, so the common way to write it is capital phi, can write phi, and here this is actually electromotive force. Just write so it all comes from Lorentz force. So we have electric field and then force due to magnetic field as well. But when we take this integral, then what happens is that for a thin wire, this is out of plane and this is on the plane, so this part actually cancels out and we only have electromagnetic forces, integration of electric field over length. Okay, so basically what we get, electromagnetic force from the Maxwell-Faraday equations. And of course that's little, we are not really discussing that, but I just wanted to recap that. And then of course we have what we have, did I write, yeah, sorry, I didn't write this. So it's very similar to Gauss's law, right? But in terms of magnetic field, and then Ampere's Maxwell's law is of course there, and this basically means total flux in a closed surface is kind of zero. Then most important, of course, Ampere's Maxwell's equations. Maybe I'll just write the equation first. Here we have curl of magnetic intensity. Here, so let me write this as and I'll write what every term means. Here H, that's magnetic intensity, and so I'll show you what it really mean and how it is related to magnetic field. Right, and so this magnetic intensity related to magnetic field, but there's another term called M, which is magnetization. In our current study, we are not actually discussing any electric field in a magnetic material, so we'll assume that M is 0. So we are just assuming M0 for non-magnetic. material. Okay. That's it, right? Then the important thing to consider here is that what we need to understand how intensity is related to all of this. So what is our goal? Our goal is to understand how medium responds to a strong electric field, how the medium property changes. What I mean by property changes is that how it shows nonlinear behavior with stronger electric field. And of course we have seen in our last class, or we have tried to argue, that we see nonlinear effects only when our electric field is very strong, right? So then only we see this chi2 e square, chi3 e cube types of terminal terms in the polarization, right? But how does the polarization actually affects the energy or intensity of light, and how it is related to everything that we have understood or studied so far? So for that we need to understand one theorem which is called Poynting theorems, that gives you energies flowing out of a surface in terms of like maybe mechanical energy, electromagnetic energy stored in the fields which is bound by the surface, and work done by polarization. So all of these things we will study one by one. By the end of the discussion we will see that energy flowing out of a surface is also function of work done by polarization. There is some polarization dependent, and that's very important. That's very central to nonlinear optics. Okay, that's why we are trying to understand this part, and let's dive right into it. So what we are trying to understand is work done. So let's go to very basics of it. Work done, integration of force times, dot product with line, or basically we'll do line integration maybe. But then what force are we talking about? We are talking about Lorentz force. So force due to electric field and magnetic field, and of course there is a velocity term, right? So let's write this Lorentz force. I hope you have already seen these terms. So we have charge dependence, of course. A charge in an electric field will experience a force Q, or charge times electric field. You all know that, I guess. Then of course we have the velocity dependent terms also. When the charge is traveling with a velocity v in an magnetic field B, then we have this, right? Then we have to do line integration. And like we discussed a little while ago, this one is out of plane. So if it is like a thin wire type of thing, and this will just will be in the out of plane, so dot product of these two will be 0. Then we are just left with charge times electric field dx. And of course we never have a single charge, right? We have a charge density, okay. And then we'll have to consider infinitesimally small charge, so we'll add the dv term, volume dependent terms, then electric field times dx. And of course we can write dx in terms of velocity dt. So now what do we have here? We have electric field term, then so we are talking about only free charges here, okay. This is charge density is free, that F means free. Then we have velocity, then volume element, then dt, okay. So basically what we get from here, this part, that free charge traveling with velocity v will give you that jf. Then we have dv and dt term, okay. So where did we see jf? We see oh, I forgot to mention that part, jf in the Ampere's Maxwell's equations, that free current density. So what we are trying to do is that we will be using all these Maxwell's equations, and so we are trying to go in that direction such that we can make use of Maxwell's equation in the current form, such that we'll have something out of it, okay. So let's bear with me for some time. So we have, for Maxwell's equation, what we had this, right? So now we have jf in the previous equation, so we can in a way substitute this. So we have the work done infinitesimally small work done. Then we have electric field, of course. Then we are replacing the free current density with then we have volume element, time element. Now we are just using some identity, and the identity is, so we are trying to replace this part. I think we have already done this type of vector algebra, right? I mean, this identity is very common. We have so everything is scalar because dot product everywhere. So then very important, I'm trying to introduce to you something called pointing vector. So what does it physically mean? I'll tell you very soon, but let's write this part. This is very important. Okay, we have got this part, and what are we left with? Okay, we have to use one more thing, that is energy stored in fields per unit volume. That is very important, right? We need to know how much energy stored in in the fields. So pointing vector will give you energy flowing out of surface, but energy stored in the field is also important. So what I'm trying to introduce to you is energy stored per unit volume. If you want to know in detail about where it is coming from, you can look up any basics of electrostatics or electrodynamics books. I'm not going to go into very details because we have to cover a lot of stuff in nonlinear optics and all, so let's just assume as it is. Now when we replace all these things in our previous equation, what we get is we had work done, we were left with this part, right? Then I'll just do one step from here. Rate of work done, we'll have this term then this is okay. So what I am trying to do here is do a integration to find total density, total energy density and everything. So here I'll again use this identity Gauss divergence theorem. So it's in volume, then we can write it in area, I guess. Yeah, so I think you are familiar with this, right? Then what we can write, rewrite this equation in terms of is we need to do some maths to find out exactly this, but yeah, I'm just skipping this part. U is energy density, energy stored in the field. Then these are left with volume integration, because here only we shifted to area integration using Gauss divergence theorem. Then we have another term, okay. So this is the pointing theorem, and let's stare at it for a while because it will tell you a lot of things. So the first term, very important, that is total energy flowing out of surface. Then second term is basically mechanical and work done, or you can think of it as, I mean, energy lost as a heat in a lot of cases. So it's basically mechanical, it's nothing to do with electrical in a way. I mean, it won't appear as a energy stored in electromagnetic wave, or electromagnetic energy flowing out of the surface and things like that. So it's purely mechanical, it can be maybe heat. Then what we have, energy stored in fields. per unit volume. Then most important part, work done by polarization. And that's in a way central to nonlinear optics, and how polarization manifests itself as, how we see nonlinear effects and how really polarization do some work, and we'll get into that. But see here, it is very simple equation that we have derived and using Maxwell's equations. Here you can see like total energy flowing in a surface, out of a surface, is also a function of polarization. So that's very important. So that's central to nonlinear optics, and how so we'll see. And of course I want to give you some practical implications, because you won't be measuring field, right? It's because fields are oscillating very fast, right? Like in terahertz, right? It's very fast. 1 micron is something like 300 terahertz. So we don't have that fast electronics. So what you see most of the time, what we see like in human eyes, we see we measure power, right? We also measure spectrum and other polarization also, we can see, measure and all. But the most important is intensity or power. So how intensity is a function of the equations that we have described. So intensity is basically a time average of Poynting vector. So this is intensity. What we have intensity, it's a time average. So this bracket says we have taken an average, and from here we can find out expressions for what I mean to say is expressions for intensity, and you might have already seen those expressions, but we are trying to go there using Poynting's vectors average. Okay, and let's take the easiest option. Let's take the easiest wave that we know, that is plane wave. We have plane wave, something we can write a plane. Okay, let me write it as, so how can we write a plane wave? So it's the amplitude, then we have a sinusoid, some phase phi, and some polarization. Okay, then omega, angular frequency, k, wave vector, and they are related by the dispersion relation. We are not discussing dispersion yet, but yeah, we'll come back here. That's kind of dispersion relation. You can you already know, right? Lambda times frequency is velocity, but there is a refractive index, right? Its velocity is not c, that's in vacuum. And so again, refractive index, I don't know you have come across it before or not. Refractive index is function of frequency or lambda, and that's why different frequencies different waves with different frequencies travel at different velocities. So that's kind of basics of dispersion, and we will discuss this later because that's very important in nonlinear optics. Okay, but let's stick to our current task, that is we are trying to find the intensity. Okay, so how do we find intensity? We have electric field. Now in order to find H, we know H is related to mu naught. Then and we had magnetization, but let's 0 for now because we are discussing for non-magnetic material, right? So we have this nice Maxwell's, one of the Maxwell's equations. Sorry. Okay. Now we just need to find the curl of this, right? So then we had in x direction, so let's forget about y, then 0 and 0 for y and z. Then from this you can find the curl, right? Then again you have to integrate with t to find magnetic field, and that part is very easy, right? You might be already familiar with that. So but we get the magnetic field, which is n I am writing all this thing in terms of uh, refractive index and c. We have cos, then from here I can find magnetic intensity. Mu naught will come, then I have cos squared. Now what we need to do, E cross H, simple. We have um, then we have cos square term, then we have to take average, right? It's because this is very varying very fast in time, we cannot measure that, so we'll see some averaging effect. So what we are left with, n omega then sorry an averaging of cos square is half, so we get intensity as so that's how we find intensity. And that there are another ways of writing it as well. Maybe we can write it in terms of, so I think you already know this part, right? Velocity and again c is epsilon naught mu naught. Here mu these are relative terms, mu naught here we have C by N, that is V, we can write V in terms of maybe that become C, right? This is different. This another way of writing this expression. So what we have, you might be already aware of this expression. That's velocity of light or electromagnetic wave in vacuum can be written in terms of mu naught and epsilon naught, and then velocity is nothing but mu and epsilon, where mu is mu r mu naught not. So from this expression we can actually find um, expression for n in terms of these parameters. So here in our most of the cases mu r relative permeability is mostly 1, so you can assume mu as mu naught. Then basically n is nothing but actually mu r and epsilon r relative susceptibility, and it's similar to epsilon r. Okay, so we can use these expressions in the intensity expression we had derived, and can be written as, I'm just using epsilon r, then we have mu naught, then writing C as epsilon naught mu naught, then we have V naught square, then we are left with half epsilon r, and epsilon naught will give you epsilon, then we are left with mu naught, and mu naught and mu are actually same, so we can write it as epsilon by mu as well, anything is fine. This is also equal to epsilon by mu. Did we leave any terms? No, that's fine. So that's the expression for intensity. What do we discuss next? So okay, then what we should now do now is that we should be familiar with complex variable. What I want to do is that write electric field, magnetic field, and everything in terms of complex variable, that is in terms of e to the power I, kz, omega minus omega t and phi, because that makes life so much easier. And that's what we'll be using in our next classes. So I'll just introduce you that part. Of course, our electric, even if we are writing electric field and magnetic field in complex variable, they have to be real, because that's a real quantity. We can, measure, or see the effects of it. So what we have is electric field real of something like some unit vector. Just write some general. Then we can use identities. And if you use the complex conjugate as well, then what we get is a real term. So that's what we will be using. And here I hope you are already familiar with Fourier transform, because that's very central to a lot of optics phenomena that we will be discussing. Then okay, let me introduce to you some basics of it, and we'll be using these expressions throughout the course. So that's Fourier transform. So suppose we have a function here. We have t or time as variable. How can we go to another function where we have omega as variable? So they are related by one of the integral transform called Fourier transform. So how we get this is we have this integration. So it's integrated with time, so we lose the time variable and get omega. Then again we need to come back to the original function from the Fourier transform function by something called inverse Fourier transform. What we have here is so these two expressions are very important, and here we want to go back to polarization and write the relation. So we were not in the relations that we were using, that epsilon naught chi e, so chi 1 or whatever. Let's discuss chi 1 for now. Here we were not discussing the variables yet, right? So let's be more precise here. Suppose we are writing polarization in the time domain. What we have here is something like this. So here time t dash is a variable, and it's at time t what we have effect of electric field through chi, electric field at time t dash, that can come from minus infinity to time t. Okay, so it's a at time t, polarization is affected by electric field t dash for all time which are less than equal t, right? It cannot be greater than t because then it won't follow causality, right? Then what we can do from here, from this expression, how can we write the same expression in the Fourier domain, right? So how can we do that? So we just take the Fourier transform, okay. So this is actually very common Fourier transform identity. So here we have polarization in terms of omega, but here this part uh, is called convolution. When we have a function something like functions to something like maybe let me write it as functions of t and g of maybe something like t dash minus t. Okay, this is actually called convolution. So what then of course the integration. So okay, here we are left with two integration. The identity is when we take Fourier transform of convolution, so we are taking the Fourier transform of this, right? Then we are left with multiplication of the function, multiplication of the, suppose Fourier transform of f is capital F and Fourier transform of g is capital G. So if we take Fourier transform of everything, some Fourier transform of convolution, we are left with only these two. So here we have epsilon naught okay. So this is a common expression from Fourier transform we have used, and you can look it up. Again, there one more thing, that chi, what I'm assuming till now, it's what I'm assuming is it's a scalar quantity, right? But that's not true. It's a matrix, or it's a tensor basically. So it's a 3 by 3 matrix called linear susceptibility tensor. Okay, then why tensor? Because polarization, suppose polarization in x direction, okay, that can be a function of polarization electric field in z direction also, in x direction also, or in maybe function of electric field in y direction. So it could be something like, let's take an example, it could be something like, just an example. So we are, let's write it in general terms. What we can write here, very general term, e of I, here I could be x, y, z, in 3 directions. We are left with summation of j so this will incorporate everything. Polarization in x direction in terms of electric field in x, y and z, and that for all y and z. So polarization in y is also a function of epsilon naught chi y x y or yz. So we are left with 3 cross 3 matrix or linear susceptibility tensor. Okay, then that's very important. We'll come back to it, and in nonlinear optics we'll see how the tensor is properties are for second harmonic generation, and we'll see some identities. Now what I want to discuss is to derive wave equation from Maxwell's equations, because we'll be using wave equation a lot. First we will derive linear wave equation, then we will go to nonlinear. We'll introduce nonlinear terms and how things are how things changes with nonlinearity, right? So that's we want to see. And for simplicity, what we want to assume is that our medium is homogeneous and isotropic. Isotropic means is that it's same in every direction. So what we are left with chi as a scalar, so it makes our life much easier. Then we already know the because this is electric flux, Maxwell's equations are written in this term. So we have then chi electric field, nothing but polarization, right? So we'll use this to derive wave equation. So let's start with one of the Maxwell's equation. You can start from something else also and derive and arrive at the same solution. So let's take this and the curl of it okay. Then we have to use some identities, right? So how to find this? It's easy because we already have the identities. Here this is important. This specific part is 0 for isotropic and homogeneous medium. Then we are left with then on the right hand side, again one more assumption, we are considering only monochromatic light. Monochrome means single color, so what we are dealing with single frequencies, so frequencies and colors. So basically what we say color is basically manifestation of frequencies, right? So So what we have here is we have a wave something like this type. If we had multiple frequencies, then we could have a integration or summation of multiple omega, something like that. But we don't have something like that. We have only one omega here. Okay, then in that case what we can do, we can replace time derivative with minus j omega. It's very easy to see, right? If we take derivative of t, we are left with minus j omega, right? So from all of this, what we are left with is sorry, actually what I shouldn't have done here is I have inserted the card inside here. It will make our life difficult. Let us keep as it is. Then we can replace it with minus I omega t, right? So here we have using this identity, and now we have j omega okay, b will be here. I can take this out. Here again we have to use another Maxwell's equation we already know. Here we are assuming this to be 0, no free charge, then left with this. In terms of magnetic field, again we have assumed magnetization is 0 because it's non-magnetic, and d we can write as epsilon naught E. So how can we write this equation? So now we can replace all of this in this equation. So what we are left with now, okay, we had j omega from our previous equation. Now again we can replace this with, so what we are left now, so let's simplify. We have omega squared E, and here we have not an epsilon, right? Then we can write again in terms of refractive index, or we can write in many ways. We can, so this part you might be already familiar, we used this expression earlier. We can write mu as mu naught as mu. This is because mu is mu naught times mu r, and mu r is 1 for us, right? Then this is nothing but uh, 1 by V, or in terms of refractive index, because V is right, so we are writing in terms of V, and again we are writing V in terms of refractive index. Okay, this will be square because we have from the dispersion equation I introduced to you right earlier. So I'll just replace everything with K, and I will take this part on the left hand side. So this is something called Helmholtz equations. There is no time term, so it's time independent version of wave equation. So the time independent wave equation. Then again we can think of it as a eigenvalue problem as well. So for that, this, you know this, right? This is Laplace operator. And here k square is the eigenvalue, and E is the eigenfunction. So this basically describes the spatial form of wave equation. I mean, we are not really looking into how it is changing with time, but we are looking into how you go from z equals to 0 to z equals to maybe 1 meter, how it changes and everything. All of this can be found from these Helmholtz equations. So that's why it's very important, and a lot of things will be derived from this, and it's very important in optics. And also it's important to note again here is that this all for single frequency or monochromatic light. Okay, now that we have learned Helmholtz equation, let's use it. Let's try to find some solutions, and let's find out why it is so important and why it is so central to optics and nonlinear optics. We will be using it over and over again as we build mathematical basis of nonlinear optics. And okay, before we go any further, let's talk about one more thing that we'll be discussing later. That's Selmayr equation. So what is Selmayr equation is, so we talked about this dispersion relation, right? Now I have told you that refractive index is a function of frequency or wavelength, right? So how to find this relation? So if you are buying a nonlinear crystal or any optical element, like even for different kind of glass, manufacturer will tell you what the Selmayr equation is. So Selmayr equation will give you the refractive index as a function of wavelength either wavelength or frequency. So Selmer equation is usually in something like in this form. And here omega z are the resonance frequencies. Here the loss is too high, or in general the Selmer equation breaks down, but away from the resonance frequencies the Selmer equation holds very well, and the manufacturer will give you some kind of equation like this, and from that you can really find out how the refractive index changes as a function of frequency or wavelength. And let's talk about some of the solutions of Helmholtz equation now. And okay, let's go back to this for a while. Plane wave equations we have already discussed, right? Single monochromatic plane wave can be written something like this. Here one terminology or one quick info I want to throw out here. Omega frequency is the optical frequency, right? So it's in terahertz, so that oscillates very fast, and there is a terminology for that. Then this is called carrier frequency. And let's assume this is a complex envelope functions A, so we can write A as this. So A is a function of position vector. So this is a complex envelope function. So what I mean by that is, suppose we are looking at a wave traveling in z directions. Now the optical frequencies will oscillate very fast. Then what A does is modulates this carrier part in a manner something like that. Okay, so it's the envelope functions, it's the envelope of the carrier. So this is a very common terminology in optics, so we'll be using it later as well. And I'm sorry, I have to throw one more terminology. So all these waves, optical waves, EM waves we are talking about, or we'll be discussing going forward in our course, are paraxial. So paraxial means near to axis. So what axis we are talking about? Suppose we have a laser light coming out, it's collimated laser light, and we have maybe lenses, something like that. Then maybe there is a nonlinear crystal, then again it's diverting and collimation, something like that. So what I mean by that is that suppose this is the axis, optical axis, then these beams are near to this axis. What I mean by that is, suppose this is the axis, the angle, the optical wave, so this is given by the unit vector that is collinear to the k vector, that's propagation vector. So the angle between the axis and the wave is very small, something like maybe less than 10 degrees or so. So all of these wave equations that we'll be talking about are paraxial, and we want to find the paraxial Helmholtz equation because that's only we'll be using throughout the course. Now what we can do, we can have this wave function, and let's use only the spatial term, because we have already taken care of the time varying function in the Helmholtz equation. So Helmholtz equation is free of any time part, right? It's a eigenvalue equation in terms of the spatial term. So what we can write here, so our um, function will be something of this type, and we want to introduce this term in the Helmholtz equation, right? So Helmholtz equation is very important because a lot of solutions of Helmholtz equation we'll be using later. One of the solution is Gaussian wave, and that's very central to nonlinear optics because a plane wave is something like it's not it's very idealistic. There is no wave that's extending. Suppose it's traveling in the z direction, so plane wave means it's extended everywhere in the xy plane, so that's very idealistic, so something like that cannot happen. But Gaussian wave is something like that that can be used to approximate lasers, and that's very practical. So we want to find all those solutions and find out what are the properties of such solutions and how we can use those solutions in our discussions on nonlinear optics. So let's plug this in Helmholtz equation. And here I want to introduce to you, so this Laplacian, these three terms, right? Now let's separate these two and this. So now we can have something called transverse Laplacian operator. So this part is the transverse Laplacian operator, and we can designate this as okay. Now we will use this because the wave is traveling in the z direction, so this z dependence will operate on that, but a lot of things they are not changing as we go in the z direction, so we can actually separate x and y. So let's solve this, then it will be clear. Now we have this transverse Laplacian operator. Then what we have here, let's take the first derivative. Okay, then okay, I'll just write it into steps. Then we have this k square term. So first we have then this, then in the second term we have this and 182 minus kz and plus k squared. So you have to take another derivative. Now if we take derivative of this, so sorry, there won't be z, so let's take derivative of a, then we will have two of these terms, so we and if we take derivative of this, we will have 1 it will be minus k square, and we have this. Okay, now we have this part, and here we have to take some assumptions. Quickly, I'll just remove this e to the power I k z part. Okay, and as you can see, these two term just cancels out, but there is more to it. Again, one more assumption. I'm very sorry, I have to I'm introducing to you a lot of assumption throughout this course, but this is very important, and you will uh, you will find it over and over again, something called slowly varying. The approximation is called slowly varying envelope approximation. So let me write it down. So what does it mean? So we had seen this very rough sketch. So here we have this carrier wave that's oscillating very fast. Then we have this envelope function. So the idea is that that envelope is varying very slow in the length scale of optical wave. So what I mean by that, so this is the optical wavelength, right? So then the envelope is not oscillating like this, so it's varying very slowly. And how to describe it mathematically? Here we can have, suppose that's del A is the change in envelope, then del A is very small than del A, so it's varying very slowly. Then delta A can be written as this. Okay, now the idea is it changing very slowly in the length scale of optical wave, that's the wavelength. So I can replace it with wavelength only. So what I have here is right. Now what I can do is, let's write it as this, or I can transfer lambda to this side, and 1 by lambda is proportional to k. So what I can write here is k times a. Now I can take another derivative. What I can have here is del a by del z. Then again this will be very small compared to a, right? Then this will be very small compared to k times a. So it's very small compared to k square by a. So what I have got here is the second derivative is very small compared to k square times a. So why it's important? See, we have this k square a terms, and then we have this second derivative as well, right? So according to this approximation, we can just cancel out this because this term will be very small. Then what we get here is very simple. This equation is very important, and this is called Paraxel-Helmholtz equation. Right. Now there are a lot of solutions to this Paraxel-Helmholtz equation, but we'll be discussing only one, that's Gaussian beam, which is very central to nonlinear optics and optics in general. And how one Gaussian beam looks like. So Gaussian beam is something like this. There is an amplitude function qz, you have rho square. So what are all these? Suppose this is a z direction, so rho is nothing but a cylindrical coordinates radius. Okay, now what we have here, q z, there are two terms. One term will talk about the phase and one for amplitude. How so? I will see. Here Z0 is called Rayleigh range. Rayleigh range is very important. So okay, quickly tell you how a Gaussian beam looks like, then you will understand why it is important, and a lot of these parameters or mathematics, it will be easier to visualize. So Gaussian beam looks something like this. Now here there is a minimum. That minimum is not zero. For example, in ray optics, when you are talking about focusing using a lens, we just trace the ray in such a manner that at the focus it's zero. That's not true. That's not physical. So in Gaussian optics there is a minimum at the focus, but that's not zero, and it's called beam radius, or I mean width or beam radius, or anything you can call it, and is denoted by omega naught. And at, so this is a z direction, so what will happen at z, this width we can use width as w. So at z equals to z naught, width will become root 2 times of the minimum width. Okay, how so? So let's go back to mathematics for a while using this thing. So what we can, so we have this 1 by q terms, right? So what I can write the 1 by q terms as, so you have these two terms. First term will give you beam curvature, second will give you wavefront radius, just a fancy name for what we have been discussing. Now complex amplitude has a very fancy long expression, but not all of it is important. We'll discuss what everything means, and we'll also try to filter out what's really important for our kind of applications. Let me quickly write it down, then we will discuss. So this is a real part, real part in the sense ki okay, we have this Z, but you can forget about it, but this part, so this part will give you how the beam looks like, how the intensity looks like in the y direction or xy direction. But then again we have this phase part. And we have few parameters which are really important, and this is what we will be using more. Okay, so these beam waist we have already talked about, right? Beam waist is the width of the beam, and why that's important is that we want to know exactly at what point how does the beam look like, and what is the spread of the beam and all. So that's really important in optics, and we want to know exactly um, how things are at different distances. That's why that's really important. Okay, Z naught I told you, right, at Z equal to Z naught, which is Rayleigh range. So here, from here you can find out, right, at Z equal to Z naught, which becomes root 2 times of the minimum value. And why it is important? Because after a while the beam will spread out, and suppose for nonlinear optics you need very high intensity, and if the beam spreads out, our intensity will be reduced, and we cannot use it for nonlinear optics because the intensity will be low and we won't get any nonlinearity at all, right? So we need to know exactly when the beam is spreading out and at what point our beam is looking I mean what's the expression for it, right? Then we have the curvature of the beam, so beam is moving like that, then at wavefront it's something like that, right? So that curvature of the beam is given by this expression. So it's the Z is now it's moving, the relation is opposite, so at near focus it will be more curved, and as it goes further it becomes more flat. So these are the trend that you need to be aware of, and that's what's more important. Then what else I need to talk about? Okay, now we want to know the relation between the width, minimum width, and the Rayleigh range. That's also very important because suppose you are given the width, then you can find the Rayleigh range and vice versa. Let's talk about the properties for now because that will be very important. And what we really need to know, one of the main property, of course, intensity. That's something we can measure, and intensity is nothing but the square of the field, right? And we have rho as x square plus y square. Now intensity for rho and z we have now a lot of things can be said, uh, can be found out using this equation. So so one thing we want to find out is how the beam looks like on the axis. That is, on the axis the rho is 0. Now what is called Gaussian beam? See, for any z, the intensity is a Gaussian function. So this is a Gaussian function, right? So that's why it's called Gaussian beam, right? And how does the Gaussian beam looks like? Suppose our z is fixed and you are looking at some rho. It has a Gaussian type function, right? That's intensity. So it has a Gaussian shape, and that's why it's Gaussian beam. And as I was talking about, we want to know how it's on the axis. So on the axis we have this expression. Now we know how width changes. Okay. So intensity on the axis will be reduced as you go along the z direction. So what will happen, suppose you have two z, a z1 and then z2 is a little higher than z3. So how our beam will look like? Initially it will look like this. More power will be concentrated around center, then it will spread out a little bit. Then what will happen, it will spread out even more. So that's very important. So that's a same way of looking this figure. That's as it goes along the optics axis or in the z direction, it spreads out, and that's very ideal, right? So I mean, ideal in the sense it's very practical, because we can model a lot of actual light sources using this. So nothing is, suppose even if you are trying to focus anything, like use a magnifying glass, try to focus something, it doesn't focus to a single point, it's focused to a very small spot but not zero, then it again spreads out. But it's this is something you see everywhere, like a lot of implication of this. Then again intensity is important. Then one more thing is very important, that's power or total power. So in order to find total power, you have to integrate along the row, and with this integration what you can find out is, oh, this is something like the area, right? And rho naught is the radius, so you have that half term. Then but what is important is that, suppose Gaussian beam is spreading like that, then we want to know, suppose we have a detector of this size, how much power will we be measuring? That's very important. Okay, now what we want to find out, that how much power we have till radius something like rho naught. So what we can, or fraction of total power, so we can write it as this, rho naught And using this expression we can actually find out what is the total power within a certain area. Suppose you are looking at rho equal to the beam waist. Okay, then from here you will see only 86% of the power is inside. Okay, that's very important, right? So as your detector size increases, your power measurement will be different. So you need to know exactly how much power you will be measuring. Then if your rho naught is maybe 1.5 times of beam waist, then you will measure like 99% of the power. So this way you can find out. Then I already talked about beam waist and all, and how it changes and what is the significance of relay range and all. But one more thing we need to talk about is that beam divergence. Let's go back to this picture. So it goes something like this, right? Here we have rho naught, but after rho naught it just diverges. So what we want to find out, suppose you can just draw a line here, something like that. So it's like a for z very larger than z naught, this increase in width has a linear relation with z. So we can find out this angle by approximating that. And what is the angle? That angle is the divergence. So we can find the divergence using this. So we can have, okay, let me change it. So what are we, let me do it completely. So that's the expression we had, right? So we have just expanded it and arrived at this approximation. And here you can see, right? So this is something like, here we have this z naught where omega will become, so this is not actually z naught, sorry, where z naught will be where this will become root 2 times of omega naught. Suppose this is where it becoming root 2 times of omega naught. So then here there will be a somewhere like here we will have z naught. So what we can do, we can use omega naught by z naught as theta, which is nothing but the divergence angle. And from the expression of omega naught and z, so we had this expression, right? Omega naught is equal to square root of lambda z naught by pi. So we can just replace it here. And we can arrive, so this is the theta, and using this expression we can write theta as lambda by pi omega naught so divergence angle and this expression is very important because one thing we can find out here is that suppose your beam waist is, or beam waist is not what we have, that minimum radius is called beam waist, right? Omega naught. So if beam waist is very small, then your divergence will be higher. If your divergence is smaller, then your beam width is higher. So what we can like visualize, suppose your beam width is very small, it will move something like this. Suppose you are doing a tight focusing, then you can have something like this, which is diverging even more. So that's very important. And I think that's it. Of course there are more parameters we haven't talked about, phase and all, but yeah, we will discuss things as we need it, as we go along in the course. That's it for today. And so that's a few of the basics of linear optics. From next class onwards, we'll try to understand we'll try to go through the basics of nonlinear optics. We'll be using Helmholtz equation and all the basics that we have built up in the current course, and yeah, then we'll use it for the formulation of nonlinear optics.